Hi, how are you? In this video I will explain how to build a 3D printed brushless Halbach array motor. Most of the work is quite simple and parts only need to be 3D printed and then assembled in the correct sequence. Winding the copper wires isn't much more complicated, however it will require some more time and careful working. To get started you need to purchase all the required hardware. Large neodymium magnets, smaller neodymium magnets, enameled copper wire, small ball bearings, a large ball bearing, a shaft collars, threaded rods and a bunch of nuts. Depending on your application, you should prepare M3 bolts and nuts, washers, connecting cables, heat shrink and plugs. As tools you need a decent drill press, a solder iron and various screwdrivers. Make sure your 8mm drill bit is in a good shape. After downloading the STL files, 3D printing can be started. Basically, the motor consists of 3 main components, whereas each component is divided into 2 halves. There is the rotor, the stator core, and the stator mount. All parts can be printed with 0.15mm layer height. Except of one part, there is no support material needed. The rotor with the slots for the magnets is the largest part. The second part of the rotor is like the lid of a jar and holds the magnets in place. The third smaller part of the rotor, named collar, is needed to firmly lock the shaft to the rotor. Use PETG for all these parts. That's the material I have tested. ABS maybe works as well, but you probably need to experiment with shrinkage. The rotor needs to sustain high centrifugal forces, hence I recommend 4 shell layers and 50 to 70% infill. Since it takes several hours to print the rotor, I recommend to first print this small section, fit the magnets and tune the print settings if needed. The shaft collar is the only piece which needs to be printed with supports enabled. The stator core is the winding form of the copper wires. It consists of 2 symmetrical parts. I recommend to use magnetic-pla from Protopasta. PLA has a problem at higher temperatures, but the metal powder not only helps to increase the magnetic flux, but also helps to dissipate heat. 2 shell layers and 95% infill are recommended. The stator mount is also divided into 2 halves. It firmly locks the stator core and allows to mount the motor on a chassis. It is printed with PETG like the rotor. Printed with 3 shell layers and 70 to 90% infill. After all parts are printed, they temporarily should be assembled and may be cleaned up. Use a drill press to adjust the holes for the shaft and the screws. Lubricate the drill bit and drill at low rotation speeds. Cut and not melt the plastic. Press in all the ball bearings. If it's too loose, you can add some Kapton tape, but don't use painter's tape. Fix the nuts on one end of the rods with threadlocker glue. Push the 2 halves of the stator cores onto the stator mount and align the teeth headers. Fix them with painter's tape for later winding work. Now the wires need to be prepared. Enameled copper wire with 0.45mm diameter is needed. 6 strands are combined into a single cable. It needs to be 5 meters long. Twist it 20 to 30 times and wind it up onto a small spool. The copper wire of one spool will weigh roughly 50 grams. 3 spools are needed for winding the 3 phases. I recommend to wire the motor with the Y configuration, hence the 3 terminals of the cables can already be soldered together and isolated with heat shrink. If you want to experiment with delta or Y configuration, keep all the terminals unconnected. The stator with all the wires looks like this. The 3 phases are colored in yellow, red and blue. The cables are placed with alternating phase and direction into the slots. A single phase consists of 9 smaller coils arranged around the stator. Now let's start winding. Grab the first cable, phase A, and place it into a slot which has a tooth head. Fix the loose beginning of the cable with some painter's tape. Bend the cable into the direction suggested by the tooth head, skip 2 slots and place it beneath the neighbor tooth head into the third slot. Use a piece of wood or plastic and tightly push the copper wires into the slots. Never use a metal tool like a screwdriver because it damages the isolation. Better use my 3D printed wire pusher. Wire the cable back to the slot where you have started. The first turn of the first coil is now completed. Repeat this procedure and make 3 more turns. With the last turn, place the remaining cable inside the stator. It will stay there until the next round. Now get the second cable, it's phase B. Repeat exactly the same as with phase A, but start with 2 slots offset. The overlapping wires will help to fix the wires beneath. When done, also put the spare cable inside the stator. Redo the same pattern with phase C. Great, 1/9 of the winding work is now finished. The rest of the work isn't much different. Get the spool of phase A out of the interior of the stator and continue. Then do phase B, then C, and so on. When you get to the very last coil of phase C, you will realize that there is something fishy. The cables need to be wired beneath the first coil of phase A. Widen the space with a wooden toothpick, unroll the remaining cable from the spool, and start weaving. The result of the weaving work not only looks great, but it also secures all the cables. Now it's time to insert the stator mount. Feed the 3 begins and the 3 ends of the cables through the holes. You probably need to bend the windings outwards in order to avoid jamming them between stator mount and stator core. Make sure the 2 smaller ball bearings are well inserted. Also insert the 4 threaded rods with the nuts glued on one side. Be careful to not damage the isolation of the copper wires. If you soldered already the cables for the Y configuration, there are only 3 wires to feed through the holes. For finishing the wiring, you need to solder some connectors and protect them with heat shrink. Well done, this was certainly the hardest part of the motor. As next we are going to insert the magnets into the rotor. The problem is the variation of the quality of these magnets. They are differently strong and heavy, and this could cause a badly balanced rotor. Therefore we are going to measure the weight and the force of all magnets. Our main tool is a little scale. The absolute accuracy is not as important, but repeatability needs to be good. Stick all the large magnets on an iron bar. Orient them with the same polarity, north or south upwards. Label the magnets with a number for later identification. When measuring magnets with a scale, we have to be careful to not disturb the result by magnetic components of the scale itself. Avoid any magnetic objects on your desk. Even a screw hidden inside a table could corrupt the numbers. This is a simple construction for measuring the force. Take a wooden bar and put one end onto the scale and the other end on a block of wood. Place the magnet on the bar, mark the exact position and tear the scale. Push a ferromagnetic object beneath the magnet. Also remember or mark that position. I found a piece of ferrite with a similar size like the magnets. Another chunk of metal, for example some nuts, will certainly work as well. Tear the scale for each magnet before measuring the force. Make a note of all the values and select the 18 strongest magnets. For measuring the weight, I'm using a similar construction with a wooden lever. This time the scale needs to be turned only once without the magnet. Also write up all these values. The plot illustrates the distribution of my magnets. The variation of the magnetic force is very significant, but it has no influence on the centrifugal forces. However, the variation of the weight matters. Imagine if all the heavy magnets were located on the same side of the rotor. For this reason we are going to insert the magnets with a special pattern. The picture shows the 18 positions of the slots for the main magnets. But these numbers are not the identification numbers of the magnets from your notes. They indicate the weight. 1 is the location for the lightest magnet and 18 is the location for the heaviest magnet. When inserting the selected and sorted magnets into their designated slots, their polarity needs to be alternating. The label on the magnet helps to identify the correct orientation. If a magnet was inserted wrongly, you can easily remove it by pushing a pin through the hole from the other side of the rotor. Also measure force and weight of the smaller magnets. The plot for my magnets is revealing a huge variation in force. The strongest magnet is almost 3 times stronger than the weakest magnet, and I bought them all from the same seller. For inserting the small magnets, the large magnets will help. If the polarity is wrong, the small magnet will float in its slot. Turn it around and with the correct polarity the magnet will snap into its proper position. Certainly this sorting method isn't the optimum for a perfectly balanced rotor, but it's simple and helps to avoid the worst case. Okay, the motor is almost finished. We need to do the final assembly. The collar needs to be fixed on the shaft. In fact, there is a smaller metal collar sitting inside the plastic collar. The set screw needs to be quite long and extend into the plastic collar. The collar has 4 additional holes which can be used to directly mount a pulley or a propeller. There is also a collar available with 2 internal metal collars. This version can transfer more torque from the rotor to the shaft. Insert the shaft into the rotor and fit the collar into the rotor spokes. Slide the completed stator into the rotor. Maybe you first try to close the motor without that large washer. If the stator doesn't slide forth or back, you're done. In my case, the washer was needed. Probably the clearance depends on the print bed calibration. Turn the rotor by hand and carefully listen if there is some noise from cables which are touching the rotor. Remove the stator again and find the reason. Cables are maybe not properly in their slots, or maybe the cables are touching the ring of the rotor. Basically the rotor is already well fixed, but if there is a heavy load directly attached to the shaft, I recommend to fix another metal collar on the side of the stator mount. I also strongly recommend to build a simple wooden test stand for the motor. The 4 threaded rods are used to fix the stator. Don't tighten these nuts too much, because there is only plastic on the other side. If the nuts come loose while the motor is running, you should use locking nuts instead. Connect the 3 wires from the motor to a regular ESC. I'm using my homemade Arduino-based servo tester for generating the control signal. It is also a good idea to alternatively use an RC transmitter and a receiver. Then you can do the tests from a safe distance. For the very first test, you should really use a battery with a voltage much lower than the nominal voltage of the motor. The motor will spin not as fast, and in case something goes wrong, the damage is less severe. With 8 volts from the battery, the motor should be slower than 2000 RPM. Without a load, the motor draws much less than 1 amp. I'm attaching a propeller and let it run in reverse direction because I want to test the current and not the thrust. For this test I'm using again the small battery. With the big battery I decided to go outdoor. I hope you enjoyed building this motor together with me, and I'm really curious to see your applications. Feel free to post comments and also check the links in the video description.